Welcome back, and in this video we're going to take a brief look at damped harmonic motion and resonance. Both of these topics are largely conceptual on the AP Physics 1 exam, and so there's not going to be much in ways of mathematics associated with it. So the first thing we're going to look at is damped harmonics, and basically what it means is what we can see in our image here. And that is that the amplitude of oscillation is going to decrease in time because there's some external force which is taking energy out of the system. And remember that energy is proportional to the amplitude squared, and that's why we see it decreasing in time. So with each oscillation, the energy is going to be taken away from the system, as indicated by the amplitude. If the damping force is small, like we have here, then you're going to get many oscillations. So a pendulum swinging in a normal atmosphere, it's going to go through many oscillations before it finally comes to a rest. The carts on the track, when we have the springs attached to it, again, it goes through many oscillations, but not as many as the pendulum. So the damping force on the cart is going to be larger. So this is the situation that I'm displaying right now where the damping force is rather small, and this next image I'm about to show you is when the damping force is large. Now in this image you can see that we really only went through one oscillation, and that's about it. Okay, so we got one and a little bit of change. But this is still a situation of underdamped because we went and exceeded our equilibrium position. One of the things that can happen is that you can have a situation where the damping force is just right, such that you reach the equilibrium position in as short a time as possible without overshooting the equilibrium position. And so that is called critically damped. So what we have right now is underdamped. Okay, so the first type of damping we see is underdamped. And underdamped has many oscillations, but decreasing in amplitude as time progresses. The second type is critically damped. And critically damped on the graph would look something like this. Okay, that would be critically damped. And then finally, we have what's called overdamped. And overdamped is whenever it takes a very long time for the object to reach its equilibrium position. And so that would be a graph that looks something like this. Okay, so this one is overdamped. And this one is critically damped. Okay, the next thing I want to talk to you about is resonance, and resonance is just the opposite of damping, and that is that you take a small force and you continually push on the object at just the right rate or just the right frequency so that the amplitude increases with time. And again, we're adding energy to our system, which is going to be indicated by the increasing amplitude of oscillation. So we've all experienced resonance, or at least most of us have as children. Whenever we get onto a swing set, we are basically pendulums, and as you kick your legs forward and backwards and forwards and backwards, you're giving yourself a small push at just the right time. So resonance is going to add energy to the system. In order for resonance to occur, the frequency of the driving force must be equal to the natural frequency we give it F naught, and the natural frequency is that frequency at which something naturally vibrates. So for a spring, the natural frequency is going to be equal to 1 over 2 pi times the square root of k over m. And for a pendulum, the natural frequency is going to be equal 1 over 2 pi times the square root of g over L. We have our maximum amplitude when the difference, when we have delta F, okay, when the difference is small for the frequency of the driving force minus the natural frequency. When that's a small value, you end up with large amplitudes. And the bigger that difference is, the smaller the amplitude is going to be. This is an example of a forced vibration, and there are many other examples that we see in real life. For example, the Tacoma Narrows Bridge collapse in 1941, Galloping Gertie it was called. You can search that on YouTube. That was a very dramatic example of resonance. Now, you will create resonance in systems whenever the frequency of the driving force is approximately equal to a whole number multiple of the fundamental frequency or the natural frequency. But this isn't going to be true in all cases, and we're going to actually prove this in another video, that the resonant frequencies are going to be a whole number multiple of that fundamental. So springs and pendulums, they've only got one resonant frequency, and this is the one that you have to meet. Okay, in the next video, we're going to take a look at mechanical waves, and that's going to lead us into some very interesting discussions about the way waves behave, what their purposes are, and some of those things that we can do with them.